We previously encountered the Möbius function mu, the Dirichlet convolution star, the unit with respect to Dirichlet convolution epsilon, and we proved the formula 1 star mu, where 1 is the constant function evaluated to 1 star mu is equal to the unit. And from this we derived Möbius inversion, which says that if f star 1 is g, then f is equal to g star mu. So this is Möbius inversion. We also encountered Euler's totient function, phi. This is Euler's totient function. And we encountered it in the study of multiplicative groups modulo an integer. So in the study of the multiplicative groups Zn. Here we'll study more properties of the Euler totient function and how it interfaces with Dirichlet convolution. In particular, we will prove the property that the sum over divisors of n of the Euler totient function evaluated at those divisors is equal to n. We'll prove this property in two essentially different ways. So first, to recall that phi of n is the number of integers between 1 and n, such that their GCD with n is equal to 1. In other words, such that they are co-prime to n. Then let's start the first proof. Let's consider phi of n over d, which is nothing but the number of integers such that they are smaller than n over d. I should say d is a divisor of n, such that the GCD of k in n over d is 1. But this is the same as the number of elements k tilde, such that 1 is smaller or equal than k tilde is smaller or equal than n, and the GCD of k tilde and n is equal to d, because we can just take k and multiply by d to get k tilde. So let's then prove the property. We have that the sum of divisors of n of phi of d is nothing but the sum over divisors of n by n over d, because as we run over the divisors, as d runs over divisors, n over d also runs over divisors. And then we use the above property to say that this is equal to the sum from k is 1 to n, where we count the guy when the GCD of k and n is equal to d, because that's this number phi n over d. Then we exchange the sums. I write that this is equal to k is 1 to n sum d divisors of n. GCD of k and n has to be d. But then for each k, there's exactly one divisor, d of n, such that this condition is true. So therefore, the last part is equal to k is 1 to n 1. And then, of course, this is just equal to n. And therefore, we have proven the property. So this was the first proof. The first proof can be presented in many ways. So 1 prime goes as follows. We can consider every element of the cyclic group Zn. It will generate a subgroup of Zn, which is given by Zd, where d is a divisor of n. And actually, for instance, Zn is precisely generated by phi n elements in Zn, and Zd is generated by precisely phi d elements, and so on. And so when we sum over all of these possible divisors, phi of d, then we get all the elements of the cyclic group. A third equivalent way is to consider the multiplicative group of all roots of all nth roots of unity, and the primitive dth roots of unity. So this is basically the same group and consideration as we just did, which is again basically the same considerations as we did previously. So this is one proof. Now a second proof goes through the observation that we just proved that phi star of just the constant function 1 is equal to the identity function, which maps n to n. And then by Möbius inversion, we have that phi is the identity convoluted with the Möbius function. This is by Möbius inversion. So we might as well prove the second equivalent formula that says that phi of n, which is equal to n times the product of the prime factors of n, 1 over 1 minus p. This is a formula for the Euler Totient function, which I've discussed in my video on the multiplicative group. So if we have this formula, then this, if we expand out the factors, we just get that this is a sum of the Möbius function of the divisors of n divided by d, because, well, each prime only can occur once, and we indeed have that the Möbius function for k larger or equal to 2 of a power of a prime is equal to 0, and moreover the Möbius function of a prime is equal to -1, and then moreover it is multiplicative. So if we expand this out, then here we have all the divisors with different primes, and moreover the number of divisors is, when it is even we get +1, when it is odd we get -1 from the Möbius function, and if there's a square then we get 0. So indeed if we expand this out we do get this expression, and this is nothing but the sum over divisors of n over d mu d, which is indeed equal to the identity star mu. So phi is identity star mu, and we have given a second proof of the formula. An extra is to, for instance, take the first proof and generalize it as follows. If we sum the divisors d of n, d times phi of d, this is equal to the sum from k is 1 to n of the greatest common divisors of k and n. So it's a small exercise to try to prove this. So in summary, phi is equal to identity Dirichlet convoluted with the Möbius function is how the Euler Totient function interfaces with Dirichlet convolution and the Möbius function.